What we have on the screen here looks like quite a bit. Let's walk through it. We're considering an initial value problem of the form x prime equals af plus f of t. And we have an initial condition x at t naught is equal to x naught. These are column vectors. We are already used to the form of x equals phi times c plus phi times the integral of phi inverse times f. The change here is that the integral is now a definite integral from t naught to t, where t naught is related to our initial condition. And then in the integral, we're using s, a dummy variable. Now remember, our initial condition gives a value of x at t naught. Phi contains functions of t, so t naught's going to be replacing those in phi. But in the integral, if we're integrating from t naught to t, and t gets replaced by t naught, the integral goes to 0. All that's left is x equals phi times c. In an initial value problem, that c is what we're looking for. So x of t naught is equal to phi at t naught times c, the column vector of constants. Multiplying both sides of the equation on the left by phi inverse of t naught gives us exactly what those constants are. C is equal to phi inverse of t naught times x at t naught. That's the information that we have in our initial condition there. So the form of equation that we have is x equals phi times c plus phi times the integral from t naught to t of phi inverse times f. Before we let this get too confusing, let's jump into an example. Our initial value problem is x prime equals 1, negative 1, 1, negative 1x plus the column vector 1 over t, 1 over t, and the initial condition is that x of 1 is equal to 2, negative 1. As you can easily confirm, a minus lambda I is 1 minus lambda, negative 1, 1, negative 1 minus lambda. Finding that determinant, setting it equal to 0, gives us that lambda equals 0, a repeated eigenvalue. Then our system becomes 1, negative 1, 1, negative 1 times k is equal to 0, giving us an eigenvector of 1, 1. Since we only have one eigenvalue, we use k to find p. So 1, negative 1, 1, negative 1 times p is equal to 1, 1. That boils down to the equation p1 minus p2 is equal to 1. And we're going to go ahead and let p2 equal 0. Then we have that p1 is equal to 1 and p is 1, 0. It would be good for you to pause it here and write down the complementary solution. I'm just going to go ahead and do it. X sub c is equal to c1 times 1, 1 e to the 0 plus c2 times 1, 1 t e to the 0 plus 1, 0 e to the 0. Putting this in the form of phi times c, we have the matrix 1, t plus 1, 1, t times c. That gives us our fundamental matrix phi, which is 1, t plus 1, 1, t. And as we can see here, the determinant of phi is equal to negative 1. Go ahead and confirm that. And phi inverse is then negative t, t plus 1, 1, negative 1. We need phi inverse times f. And remember, f is 1 over t, 1 over t. So what we'll end up putting into the integral is negative t times 1 over t plus t minus 1 times 1 over t. That boils down to 1 over t. 1 times 1 over t minus 1 times 1 over t thankfully gives us 0. Ordinarily, we would integrate that with respect to t, but remember what we have is a definite integral, the lower limit of which is t naught. In our problem, t naught is 1, the upper limit of which is t, and then the variable of integration is s. So this becomes the integral from 1 to t of 1 over s0, that column vector, ds. That's going to give us natural log of s0 evaluated from 1 to t. All right, a couple of things. I don't have the absolute value around s because our lower limit is 1, and I'm assuming that t increases. Second, yeah, the 0 really does integrate to c, but we have a definite integral, and the definite integral of 0 is always going to be 0, so I'm just not bothering. Evaluating the natural log of s at t and then the natural log of s at 1, well, natural log of 1 is 0, so this becomes natural log of t 0. Now remember where this is going. We've just computed the definite integral. That needs to be multiplied by phi, our fundamental matrix. Phi, the fundamental matrix, times the natural log of t 0 is equal to 1 t plus 1, 1 t times the column vector natural log of t 0. From that, we get the natural log of t, natural log of t. That's actually x sub p, and we're going to set that aside and pick it back up later. For now, though, we have this phi at t times phi inverse at t naught times x at t naught. Phi at t is just letting us know we should be expecting functions of t in there. Phi inverse at t naught, well, we found phi inverse somewhere along the way here. It was negative t, t plus 1, 1, negative 1. And remember that t naught is 1. So phi inverse at 1 is negative 1, 2, 1, negative 1. X of 1 was given to be 2, negative 1. So phi inverse of 1 times x of 1 is equal to negative 1, 2, 1, negative 1 times 2, negative 1, which is going to give us the column vector negative 4, 3. That is our column vector of constants. We just found them using the initial condition. Finally, we know that x of t is equal to, just to remind ourselves, phi times c plus x sub p. So in this case, x of t is equal to 1 t plus 1, 1 t times negative 4, 3, that's in place of c, plus natural log of t, natural log of t, that's our x sub p. Multiplying phi of t times c gives us that x of t is equal to the column vector 3t minus 1, 3t minus 4, plus natural log of t, natural log of t. And as you can see, this one cleaned up pretty nicely despite the hideous formula that we saw.